And we're back to the Python Institute, this time with lab number 4.1.3.9, and we are talking about prime numbers. So let's go ahead and dig in to see what they have to say here. The objective: familiarize the student with classic notions and algorithms and improve the student's skills in defining and using functions. So the scenario: a natural number is a prime if it is greater than 1 and has no divisors other than 1 and itself. This might be complicated. Let's see. For example, 8 is not prime as you can divide it by 2 and 4. 1 and 8 don't count. Yes, you could divide 8 by 1 and you can divide 8 by 8, but those don't count as far as prime numbers. On the other hand, 7 is a prime number because you can't find any legal divisors. That's an interesting term, but you can't find any divisors for 7. You can't divide 7 by 2, by 3, by 4, by 5, 6, or that's about it. So your task is to check whether a number is prime or not. So you need to create a function called isPrime, and we see we already have a skeleton right there. It takes one argument, which is the value to check, and then it returns true or false, depending on whether it's prime or not. And you can see that they've already given us some code here that does a range of 1 through 20, and then tries to do a prime, isPrime, and prints the output for us. There is a hint here. Try to divide the argument by all subsequent values starting from 2 and check the remainder. If it's 0, you cannot be prime. Think carefully about when you should stop the process. So basically what that means, if we try, say, with the number 7. So let's start with 7. What we'll do is we'll basically do 7 divided by 2, or more specifically, 7 modulus 2. Now, if I try 2 into 7, 2 goes into 7 3 times. 3 times 2 is 6. So that means I have a remainder of 1. Because I have a remainder of 1, that means that I cannot divide 7 by 2. All right. So 7 modulus 2 gives me 1 remainder, which means I cannot easily divide 7 by 2. I could then try to divide 7 modulus 3. And if I try that again, 7 modulus 3 gives me 2. 2 times 3 is 6. Again, I have a 1 as a remainder. Okay, that didn't work. 7 modulus 4. Well, let's see. 7 divided by 4. That's really 1 with a remainder of 3. Maybe 5. Well, that's 1 again. Remainder of 2. And then 6 would be 1 with a remainder of 1, and then 7 doesn't count. So basically what I could do is I could cycle through all of these numbers, and I could try to divide by those numbers, starting at 2, going up until my target number, in this case 7, to determine if I ever get something that comes back that is fully divisible by that number. For instance, if I try that again with, say, the number 8, well, I tried to divide 8 by 2. 2 goes into 8 4 times. 4 times 2 is 8, which leaves me with 0 as a remainder, so it is wholly divisible by the number 2. Therefore, this is not prime, while the 7 was prime. So I could definitely do this, and that's maybe not the most elegant way to do it, but it's a way that works to begin with. So the process I'm going to do basically is I'm going to start off with a number, and I'm going to start off by creating a range, I guess. A range starting at 2, going up until that number. And then I'm just simply going to try to divide my value, or more specifically, modulus the value, other way around. So I have my number, and I'm going to check the modulus of that against my value and see if it is equal to 0. If it's not, then the range will then increase and I'll go again and again. So let's see how I might do that. So in my isPrime function, I'm going to start off with just a number, and it tells me here starting from 2. Okay, so if I remember correctly from my basic math classes, they called that number the divisor. And I'm going to start with the number 2. And then I'm going to say, well, while, let's see, a couple of different ways I could do this. Let's do a while loop. I haven't done this way before. How about while the divisor is less than my number? I'm getting the number as an input to the function, so I'll say while divisor is less than the number. And in this case, if I get 7, 2 is less than 7, so it will continue on. What I'm going to do is I want to check to see if I can divide by that divisor properly. So I'm going to say if num modulus divisor is equal to 0, then return false. So if I can divide the number by the divisor. So for instance, if I get 8 in there, I can divide 8 by 2 with a remainder of 0. If that is true, then that is not prime, and I want to return false. Otherwise, what I want to do is I want to add to the divisor. So simply divisor, yes, plus equals 1. At which point it will go ahead and go back up through the loop with an increased divisor, in this case number 3, and try the loop again. And then number 4, and then 5, and 6, and so on until it finally becomes equal to the number, at which point I then can finally say, no, you are not divisible by any of those numbers. I then want to return true. So let's see if this works. Name false is not defined. I did a typo. It's always a typo. And in this case, it's because I did a lowercase f. You probably saw that. You probably like, oh, no, don't do that. Okay, so let's see. Let's run that again, make it a little bit clearer. So the expected output is 2, 3, 5, 7, 11, 13, 17, and 19. And we have 2, 3, 5, 7, 11, 13, 17, and 19 right there. So it actually went through each and every single number in the range of 1 to 20. And it ran those numbers through the isPrime function, and it divided each of those numbers multiple times to be able to determine if it was divisible by a number or not. And these are the numbers we came back, and yes, 2 is actually a prime number, believe it or not. But it took its time. This may not be the most optimal method because we're going all the way up to num. That means for the number 19, the very last prime number, it had to divide by 1, and then 2, and then 3, 4, 5, 6, 7, 8, all the way up to 18 before it found out that no, I couldn't find anything to divide by, so now I'm going to go ahead and return true. Now, there are a couple of ways we can optimize this. For instance, something is either divisible by 2, or it has to be something less than half of the value of num. So for instance, the number 8 is divisible by 2, which returns 4. The number 19 is not divisible by anything greater than, say, 8, because that's half of its value. So what we should be able to do is go ahead and change this maximum number right here. Instead of saying num, I should be able to say num divided by 2. That should speed up the process a little bit more. Now, we're not necessarily going to notice anything in this case. Oh, we do notice something in this case. 4 is no, that is not correct. Maybe like that. All right. Yeah, no, that shouldn't work. That's absolutely right. But there are ways to be able to optimize this. And in fact, if you look into it, the maximum number that you should actually be able to go through is somewhere around the square root of that maximum number of the number that you're looking for. And if I remember correctly, it's somewhere around 1 plus the square root. You'd have to do the math for it or research it elsewhere, something along those lines. But so anyways, that one wasn't too difficult. Really trying to figure out just the fact that we just want to divide by 2, then 3, then 4, then 5, then 6, and so on. That was the hard part. Otherwise, it was pretty simple. I could have done this as far as a range or a for loop or lots of different options. Really is up to your own personal preferences. I always like to try something new.